Hello, my name is Amy Rennell and welcome back to Teacher's Corner. Today we're going to be having a little bit more of a look at the distribution side of the randomness module. So let me open up share screen and there we go. Okay, so as per usual, the problem tab is mostly for you lovely teachers to give you a bit more of an idea as to why I've even written this and come up with the exercises. We've got a few learning aims. We want to consider how random events might be expressed over an area. In particular, this is a slightly different way of exploring randomness. Rather than it being in sequences, which we see all the time, this shows randomness in a slightly different way, underpinned by distributions. We also want to explore the relationships between small samples, large samples, and distributions, consider how randomness can affect waiting time, and recognize the process of random sampling. Today, we're only going to be having a look at spatial randomness. Now, this page might look a little bit different depending on how long it's been since I recorded this video and you're watching it, but hopefully it's mostly the same. So spatial randomness, as I say, is slightly different from sequential coin toss based randomness. It also lends itself to some more interesting examples. In this case, we're going to be looking at raindrops. So imagine that you're watching the rain as it falls on the paved stones outside. The paved stones make a 4x5 grid comprising of 20 squares. Discussion time. What might 50 raindrops on the paved stones look like if they left a mark? And what kind of assumptions might we make? Now, at the moment, these some examples doesn't have a link to it, but I'm hopefully going to be recording some examples of the discussions that students might have. So if this ends up being a take-home exercise for students, they could discuss things with their parents, with their grandparents, siblings, friends, it doesn't matter. If they got a little bit stuck, they would also be able to have a look at an example of a discussion that they might have. So for example, these assumptions might be the direction of the rain, things that are getting in the way, how much it rains, the size of the raindrops, all sorts of things. Once they've discussed that, it would be great to consider how you might simulate that. So we are going to go on to a little bit more of the simulation type processes. So depending on how your students go, they might have a bit of difficulty thinking about how they simulate this. It doesn't have to be with technology. It could be as simple as watching the rain outside, simulating it by just recording observations as it's raining outside. Maybe they're dropping counters from a chair. Maybe they're, I don't know, using a dice to roll and see where on the grid we're going to mark a raindrop. Or of course it could be through code, which is of course how I have done the examples that follow. Okay, so we're going to have a bit more of an explore of the kinds of distributions that we could use to create these spatial plots. So the plots represent the paved stones and the dots are the 50 raindrops. For each plot, we want to discuss some of these assumptions. What could be going on? If this was what the rain pattern looked like, why? What could be getting in the way? What could be changing how it lands? Okay, so we're going to, for example, make this one full screen. And as we can see at the moment, we have the first example of the exponential distribution. And we might start here with some thoughts about how these raindrops might have come to be. So for example, I'm seeing across this top bit and down the side, maybe something's in the way, a table, a chair, the building, something's stopping the rain from landing in these positions. So if we run through it, I should slow this down. just so that we can see it really clearly. We've got the different iterations of this. And if I hold it here, the grayed out dots are the previous examples. So we have a bit of fuzz going on so that we can see sort of where most of the raindrops end up landing using this exponential distribution and some of the more unusual spots that it lands. So it goes through this in about 10 iterations of, so 250 observations all up. And we can see this is our last example in the yellow. There's some gray dots out here, but still this section up here doesn't seem to be rained on at all. And indeed, most of the rain seems to be around this bit down in the bottom corner. So we might explore some reasons as to why that is the case. Maybe it's coming down a downpipe and it's splashing in this bit here, and then a few raindrops are coming out the other side. Not quite the example that I had set up, but yeah, that could be an example as to why we're seeing what we're seeing. The next one we've got is the normal distribution. Again, we'll slow this down to make it easy to see. Wait for it to load. There we go. We've got the grey dots being previous examples and the yellow ones being the current iteration. So as we can see with the normal distribution, they're landing mostly in this middle circle. There's not really any in any of the four corners, although this guy out here is a bit far. Some of these guys are too. So it's not unusual for things to end up splashing out that far, but most of it is centered in the middle. So perhaps we are looking at, I don't know, maybe we've drawn a circle on the page stone and we're looking at just that middle circle. Maybe we're, maybe we have a camera set up and we're looking at where the raindrops land, but because we've got the camera set up, it's only landing in certain areas. It's a little bit hard to come up with a reason as to why the rain might be falling in one spot in particular. The uniform distribution. So our first iteration, we can see there's a few patches going on. So maybe there's a few trees or something in the way. And if we hit play, we can see it starts to build a little bit further. So here's the second run. Let's go back and have another look. This one, there we go, that's better. So we've hopped to the end and we can see that there's rain pretty evenly across the different sections of the grid. Of course, we've got, it's a 20 by 20 square. So we're looking at, yeah, fairly even, a few patches, which is probably what we'd expect if the rain was coming straight down with nothing blocking it. This one, we're looking at the Poisson distribution. Let's have a look at this one. So this is the Poisson buildup, and we can see that they're all in nice straight lines. It's very grid-like. Rain doesn't typically fall like this. In fact, the Poisson distribution is not a good example for these raindrops landing. The Poisson distribution is great for looking at the number of events in an interval, but certainly not spatial randomness. So which distribution do you think works best? I'm a huge advocate for the uniform distribution. Now would also be a good time to talk about the difference between the uniform distribution and the constant values. So some trouble that I'm aware some students might have is the confusion between what it means for it to be uniform and what it means for it to be constant. If it was constant, for example, it's always landing in the square 5, 5 constantly. It doesn't shift from there. Of course, we are wanting it to be an even spread. So some of this discussion we'll add in here is going to be about the different distributions and what they're used for and what they mean. So of course the uniform distribution is equal probabilities across all options. So we've got an even spread of raindrops. Our next exploration goes into more of the short run and long run simulations. So before playing with a slider, what distribution do you think this might be? And since having a look at the distributions already, we're probably leaning towards the uniform distribution. We can see that it's not all in one area, it's not got lines. It could be the normal distribution, but we're leaning towards the uniform distribution. And as we have more and more observations, we can see, yes, it builds into pretty obviously a uniform distribution. And some examples, again, talking about some different discussions that might be had around spatial randomness ideas. Okay. That will be all for this one, and then I will do another video about how we might look at the waiting time distributions. In particular, there's a few different areas that we can explore, including using some other tools that have been developed at the University of Auckland. See you then.